Now that we understand from our discussion last time the force on a charge moving through a magnetic field, I want to now take a little bit more of a macroscopic view and ask what happens, because we often don't deal just with a single charge moving. Usually we have charges moving through a material or in some kind of a wire. So I want to ask not about the force on a single charge, but actually the forces on a collection of charges, such as we might see in a wire. So to get our thinking really started on this, I'd like to consider a diagram of some generic situation. So maybe I've got some kind of thick wire or chunk of material with some strange shape. I'm going to make it here shaped like some kind of a horn or something. I'm not sure exactly what this shape here is supposed to be exactly. And that shape then is going to be immersed in some magnetic field. So let me sketch some magnetic field vectors, which will eventually become some sort of magnetic field lines that we'll learn about later on in the course. So there's some magnetic field B of R. And then inside this material, there's going to be all kinds of little charges perhaps that are moving around in here. And I want to figure out the total force from all of those movements. And of course, eventually I'm going to turn this into some kind of a big integral. But for now, I'm just going to focus on all the forces coming from the charges in a little chunk of the material. So let me draw like a little, rectangular little chunk. I'll call my chunk C, and that chunk will have a certain volume, delta V sub C, like so. And then my job is then to compute the total magnetic force. So the magnetic force, B we use to denote magnetic fields, total, that are on this object, of course, are going to be equal to then the sum over all of the charges making up the object, I, of each charge, Q sub I times V sub I, cross with the magnetic field measured, of course, at that location in space, which is affecting my particle, B at R sub I. And our job then is going to be to sum all of these pieces up. Now, what I want to do, as I've indicated here, is break that sum into chunks that I can eventually turn into an integral. So rather than maybe summing over each and every individual particle, what I will do is I will group the sum into a sum over chunks, where I want to figure out then the force on each particular chunk. And the force on a chunk then is where I simply add up all of the contributions to my final total sum here that are associated with charges that actually belong to my chunk. So there's going to be a sum then of charges I that are members of or belong to or are contained in my chunk, right, times QI VI, cross then with the magnetic field measured at the location of these particles. Now here is where I'm going to make my first mathematical statement or manipulation. We all know eventually what I'm going to do is take the limit where these chunks vanish, right? They're going to become super tiny, very small, squished down around a single point. So here I'll draw a little point that I'm going to shrink this chunk down to. I might call the location of that chunk R sub C, the location of my chunk, right? And now as this volume of the chunk vanishes and shrinks down to that single point, of course, all the particles in this chunk are basically then sitting at exactly one point in space. And so therefore, the magnetic field that they all feel will be exactly the same. It'll be basically just the magnetic field measured at that point R sub C about which I'm shrinking my chunk. So I can reduce this B then to the magnetic field just at the location of that chunk. And I can get away with that. I can perform this maneuver because eventually I'm going to allow the volumes of my chunks to vanish, and that limit then is what's going to allow me to just look at the magnetic field at the middle of my chunk. Because basically everybody in that chunk is so close to that central point, we can just take all their magnetic fields to be the same. All right, That's a very good start, because now you'll notice that this magnetic field quantity is constant for all the particles in my chunk. That was the whole point of that last argument. If I look at my sum here, notice there's nothing now about this magnetic field that depends on I. As far as this sum is concerned, this magnetic field is essentially constant. Now, as I've been stressing, the algebra of the cross product is just the same as any regular product. It obeys the associative property and the distributive property. The only thing I have to be careful about is always to maintain the order of my vectors, because it's not commutative and the sign gets flipped if I switch the order. But you'll notice by using distributive and associative properties without changing the order here, because I have a sum of a product, right? That's the same as the sum all added up first and then performing the product. In other words, I can simply put parentheses here around this term, and by the distributive property, I have exactly the same property I had before. So my job now is to try to understand what this sum gives me when I sum it just over the particles in a particular chunk. So let's see what that then becomes. So now I'm going to concern myself with what is the sum over all charges belonging to a particular chunk of the charge in that chunk times the velocity of that charge in that chunk. And I'm going to now begin to relate this to our previous concepts of flow, right? Because clearly we are looking at flow of charge here. Somehow we hope this is related to currents or something along those lines that we already understand. Now to do this, let's move up here a little bit, slide up a little bit so we can draw a nice diagram of what's going on. I'm going to draw a larger version here of my chunk. So my chunk now will appear quite a bit larger so I can think about actually what's going on inside of it. As I draw this and I think about it, there may be different types of particles here inside of my material, right? I might, for instance, have some positive charges that tend to be going off in this direction. Maybe there's an electric field driving them in that direction. So I might have all these positive charges more or less moving in the same direction because they are one particular type of charge in the system. I might have some other type of charge, say some negative ones that are moving basically in the opposite direction. They might have their own different drift velocities. Maybe there are bigger charges, so they move more slowly. It's a little bit hard to say. But the one thing I can say for sure is I have different types of charges in here. Different species will be behaving differently. So I'm going to need a sum then over what I will call alpha, where alpha here is labeling the different types of species, or if you're interested in materials, this is what would be called the carrier type. So I have different types of carriers in there. And each carrier inside of my chunk here, there's going to be a certain number of them. I will call that capital N sub alpha, right? That's the total number in my chunk. So that when I am supposed to sum over all the particles in my chunk, since all the ones of type alpha are behaving the same, I'll just get the same property over and over again n times, where n is the number in the chunk, and then what it multiplies is the charge qi on my carrier times the velocity that that type of carrier happens to have when it's inside of my chunk. Okay, very good. Now, next, we can start to understand this in terms of quantities that are more familiar to us from flow. So for instance, what do I know about? I know about the charge on my carriers and their velocities. This capital N, I can break it down in terms of something related to the density, right? That should be equal to the density of particles of type alpha, which I will call lowercase n sub alpha, times the volume of my chunk, right? That would be the total number, where little n sub alpha is the number of alpha per unit volume, like so. So let me now rearrange my sum using this new way of representing things. So that's going to equal then, this quantity I'm trying to compute is going to become the sum over alpha For capital N alpha, I'll have my density, N sub alpha. Don't forget the factor of volume. That's coming next. This has to be substituted in there for capital N. I'll get the volume at the end. There's the charge, Q sub alpha, and the velocity, V sub alpha. And this whole thing then has to be multiplied by the volume of my chunk. But the volume of that chunk, again, is a constant, right? It doesn't depend on my particular carrier type. It's just the volume of this overall chunk. So it being a constant, I could pull that out of the sum, and I now have something that multiplies the volume of my chunk, which is very nice because that will be very useful later when I want to turn this into some kind of an integral. Okay, so now let's look what's going on inside of my sum. I have my different species. Now this is interesting. Density times charge times velocity. That starts to feel a little bit like charge density times velocity, which I know is related to current density. So let's see if we can flesh out that relationship here a little bit. If we look at what we have here, this quantity, if I spell it out exactly, right, it's the number of type alpha, so it's the number of alphas per unit volume times the charge. That's what Q is. Q is the charge on one particle of type alpha, so that's the charge per alpha. And when I multiply these, number of alpha times charge over volume times alphas, this then is just the charge per unit volume associated with type alpha. So that would just be rho sub alpha, charge per unit volume associated with type alpha. So now we're in really good shape because look, now what I have is a sum over alpha, rho sub alpha, V sub alpha of that type, right, times the volume, capital V, of my chunk. Now, this I recognize. This is the current density associated with carrier type alpha. So that would just be J sub alpha. And all that I'm doing is I'm adding up all of the current densities from these various types of charge carriers. This whole thing is nothing other than the total current density associated with the chunk. So I would call this capital J sub C, the total current density in the chunk, times the volume of my chunk. And finally, if I'm not that worried about being precise the way the mathematicians like to, and I want to start thinking about turning things into integrals, this very clearly is some kind of current density that depends on which chunk I'm in. So I could relate that, of course, to the location of my chunk, which I will call R. And then the volume of the chunk, of course, when we turn this into an integral, R will be my integration variable, and delta V then is just going to become dV, the volume of my little chunk. So we now have a very nice replacement that whenever I see a complicated expression like this sum on I, Qi, Vi, so I'm going to write it down here as a little mnemonic. Whenever I have a sum on I, Qi, V sub I can simply replace it then with this much more manageable expression that is then ready to be turned into an integral. So that's a key relationship we will use often in this course for collections of moving charges. So I'm going to put a box around that. And the final note I want to make before we wrap up this little part of the discussion is that when I did this, notice that the total current density that I associated with any little chunk was obtained by summing up over the different carrier types the standard formula for their individual current densities, namely their associated charge density times their associated velocity.